Thank you for joining today's webinar. This is the latest installment in the series of educational materials provided by Princeton Applied Research. Today's topic is going to be localized electrochemical corrosion measurements using SVET, Scanning Vibrating Electrode Technique. So to understand where we are with localized methods, first I want to take a step back and discuss bulk electrochemical methods. So the way that electrochemical techniques are used and applied to the corrosion industry is that we'll take a voltage and we're going to apply it to a metal sample in order to drive a corrosion reaction. This voltage applied is going to cause a current to flow. That current is our measured response. And by knowing some physical properties of the material, such as the electrons per ion ratio, molecular weight, density, I can take that current and convert it to a corrosion rate. And from an engineering's perspective, that's much more useful, because that'll tell me how much material I need to build to have it last for a certain amount of time. Data coming out from these experiments are often shown in plots such as the TAPA plot up in the top right-hand corner of this slide. So the procedure, the method that we use for general electrochemical corrosion measurements are to first apply a polarization and cause corrosion to happen. That corrosion is going to cause electrons to flow. We're going to measure those electrons as current, and that's going to tell us the rate of reaction. Once we have the rate of the reaction, we can do some simple algebra to convert the rate of the reaction into a corrosion rate. But that assumes uniform distribution of the current across the entire sample surface. So by giving a little background on the bulk experiments, we can say that the potentiostat then is the device that's going to apply the voltage and measure the current in TAPA plots and LPR and EIS. But the current that the potentiostat's measuring back is an integrated current, or an average current across the entire sample. So we will take the current, we'll divide it by this sample area, and that assumes the uniform distribution. However, in those techniques, we're not able to distinguish electrons from if it's a localized event, a intense pit or several less intense pits or uniform corrosion. From a TAPA plot, LPR, EIS experiments, I have no way of discerning which method of corrosion we have there. And the reason for that is all the electrons look the same. If I'm a potentiostat and I'm just counting the rate of electrons flowing through the IV converter, I don't know where those electrons came from on the sample surface. So let's talk a little bit about local techniques then, and the value they bring beyond what we can achieve in a bulk type measurement. Local measurements are made by positioning an external measurement probe close to the sample surface. So how close when we say close? Generally, as a rule of thumb, we're looking at maybe about 100 microns away from the sample surface. So that's an approximate diameter of a human hair. So we want to be about a human hair diameter away from the sample surface without touching the sample surface. So these are non-contact type measurements. But by making the measurement at the probe then and not at the sample, it's going to give me some localized nature. Some ability to make some comments on the localized structures. And why is that? The real reason for this is spatial resolution. And so you'll hear a resolution talked about quite frequently in these types of techniques, and there's really two different types of resolutions. There is a spatial resolution, which is what is the smallest feature that I can see or distinguish between the two features, and electrochemical resolution or electrochemical sensitivity, which is what is the smallest signal that I can pull out from the background. So when we talk about spatial resolution, if we think about it just kind of a sampling volume, where is the measurement being made? On the left-hand side, what I've done here is made a gray rectangle to represent the sample and a blue rectangle to represent the measured location. So in a bulk experiment, I'm measuring all across the entire electrode-electrode light interface. Anything on my metal that's wet is being measured. Contrast that over on the right-hand side with the local measurement. Where is the measurement being made? Since it's being made at the probe, it's only measuring a subset of that large sample surface. So we'll think a little bit about electrochemical sensitivity and spatial resolution and how they're both very important, but how they generally fight each other. They generally compete. And the reason for that is if I had a very large probe, I'm going to have a larger amount of signal coming into that probe. That's going to help my electrochemical sensitivity. If I have a large signal, I can measure it more easily than I can measure a small signal. However, if I go to a small probe, that's going to help my spatial resolution. And I think we can think about this as the little blue dot on the local lines, on the local window over there. As I start making a smaller and smaller and smaller probes, that blue circle gets smaller and smaller. And so what that does is it increases my spatial resolution, but it hurts my electrochemical sensitivity. And so what we're going to discuss today also is the ability of how the role that really that good measurement electronics play in extracting small signals. And that's going to help me get a high spatial resolution with a good electrochemical sensitivity. So let's talk a little bit about general comments on positioning systems. I told you that I'm going to take a positioning system and I'm going to use it to position a probe about 100 microns away from the sample surface without contacting that. Then I'm going to use that probe and I'm going to scan in the XY plane above the sample surface. So to do this, I need a nice, reliable, high precision type positioning system. A closed loop positioning system independently verifies the position of the probe. And so what I mean by this is it will have typically some type of a linear encoder installed on one or more of the axes. And what this is going to do in the case of a linear encoder, it's going to use an independent measure as a feedback loop. If you've asked the probe to move to position 1 millimeter in the X position, in the X axis, it's going to, the motors will continue to drive the stages, and we're constantly measuring where the probe actually is. If the probe needs to go further or come back, it's going to adjust in that kind of feedback response. That's contrasted to something called an open loop positioning system. An open loop positioning system relies on a factory calibration to take the voltage applied and transfer that into a expected position. And so that it's much more valuable to have a closed loop positioning system that's giving you a reliable position of the probe. Because without being able to reliably position the probe, we're not able to be able to really make reliable measurements. But that's just a positioning system. We'll talk about scanning positioning systems then. By making a series of small measurements at different probe displacements, a data map is created. And so what I'm going to do is I'm going to have 3 parameters that I need to graph. The first parameter is going to be Y position. The second set of parameters is going to be X position. And the third parameter is going to be what I'm measuring. So in a SVET experiment, that's going to be a voltage drop. In other types of scanning experiments, that could be a localized current, that could be a work function, that could be topography. So in order to graph 3 dimensions in a single plot, I'm going to use a color map or a data map, with the color representing the intensity of the measured parameter. So the series of events that's going to happen here is I'm going to make a small measurement with my probe, then I'm going to move the probe a displacement in X, make another measurement, move it in X again, make another measurement, and once I complete the X line, I'm going to then increment it in Y and start the experiment again, and it's going to run through and make a series of intensity measurements at different XY positions. So really we can envision the scan as a series of hundreds or even thousands of different types of sub-experiments. If you think about it, make a measure, move, make a measure. So those are some general comments on positioning systems and localized techniques. Princeton Applied Research's offering is named VersaSCAN. It is a scanning electrochemical workstation. We see a picture of this here that's got the electrochemical base that is a optical table that the motors and stages are mounted to. Then a picture of some measurement electronics. Here are potentiostats, and where it's the interface of the movement of the probe from the stages and the motors with the electrochemical measurements from our potentiostats and lock-in amplifiers that work with the probes to provide spatial resolution to a series of different types of electrochemical measurements. The VersaSCAN comes with professional on-site installation and training. That includes a laptop computer to control the system. It includes the support of the entire Princeton Applied Research global network. That includes our open door policy at AMETEK for trainings and demos in the United States, Europe, and Asia. And when we this VersaSCAN really integrates the signal measurements from all the different partnered Amatec brands, and that's Princeton Applied Research, potentiostats, and the Signal Recovery for Lock-in Amplifiers and Solartron Analytical. So part of the installation and support is the unpacking of the instrument, the assembly, the leveling, the proof of concept on its samples, presentation of the fundamentals of the technique, and then some hands-on training in your laboratory. So when we talk about the positioning system, one of the key advantages of the VersaSCAN system is it's a completely piezoelectric positioning system. Piezoelectrics can move at very small distances highly accurately and with high precision. So how can we look at something as large as a 100 millimeter scan area only using a piezoelectric motor? How we do that is we use the piezoelectric motor to drive a stage. So it's not simply that the piezo is moving, it's the fact that it is using an arm from the piezo to drive a stage. And you can see in the video there's a wiggle to the arm as it starts driving the stage, and it starts inching along. So it's really a bidirectional piezo. One motion is to pull the arm away, another one is to move up and reposition the arm, and then go in and grab the stage and move it to the next position. What that does is it allows us to take the high resolution and repeatability and all the positives of a piezo and expand it to a long area travel. Contrast that to some stepper motors that are often seen with backlash and some different types of negative consequences of the way that a stepper motor turns a screw to make those positions. These are all piezoelectric systems on X, Y, and Z that are giving you 100 millimeter to travel and 50 nanometer resolutions. So here are some different types of localized testing methods and techniques. And the VersaSCAN, then, once you have the VS base in place, we can add different types of probes and different types of measurement technologies to accomplish any one of these. The one we're going to focus on for today's webinar is the Scanning Vibrating Electrode Technique, SVET. This was called Scanning Vibrating Probe Technique in other literature. The goal here is to image local currents by measuring voltage fields in solutions. Some of the key applications for this are localized corrosion, galvanic couples. Other types of techniques are localized electrochemical impedance spectroscopy, which measures the impedance and phase angles and currents of the sample. What this is very useful for is coatings and corrosion inhibitors. We have a scanning droplet cell that confines the electrochemistry to a small flowing droplet. This is nice to refresh the corrosion products. You get to take a measurement in your cell of a small subsection of your sample without cutting the sample. The next one is a scanning electrochemical microscope or scanning electrochemical microscopy. This is the most versatile of any of the techniques available through the VersaSCAN platform. And the reason for that is we're using two different potentiostats, one on the probe and one on the sample. And what that's going to do is allow you to control and monitor the redox reactions, the reduction oxidation reactions with very high spatial resolution. Some other types of localized testing methods that the VersaSCAN is capable of: scanning Kelvin probe, which is going to measure work function difference in air by a non-destructive capacitance-based method. And so what's attractive about that is you can extract a parameter that correlates to corrosion potential without having to expose your sample to any electrolyte. Also, there's non-contact optical surface profiler, which is a laser-based technique. This can be used to chart topography. It accompanies nicely, if you think about a SVET technique, using to study the intensity of pits. An OSP technique can study the depth of the pit and give you another piece of the puzzle. So I'm a trained electrochemist, and as such, the idea of SVET it benefited me to know really where it came from. Really benefited me to understand how that technique evolved to how we do it today. The scanning reference electrode technique, or SVET, has been done for decades. And the goal here is SVET uses a dual measurement probe. So we think about one probe that's got two different platinum wires. What was happening is you would measure the voltage drop between those two platinum wires. So why would you measure the voltage drop between those wires is if you look in the image in the bottom right-hand section of the screen, we'll see a local anode and a cathode material with a local anode. That's going to cause current to flow, and that's the corrosion process as current flows between the cathode and anode. Then that current flow in solution creates voltage fields. And so that voltage field is correlated to, it's a linear type relationship to the amount of current flow at the sample surface. And so we're going to take the voltage drop. If I have a big voltage drop, I have a lot of current flow, I have high corrosion rates. But you can see if we think about this as the sampling volume, spatial resolution, electrochemical sensitivity discussions we were having earlier, if my two platinum wires are very, very far apart, what's that going to do? It's going to give me a very high signal to measure the voltage drop across. That's going to give me a high electrochemical sensitivity. But if we think about the sampling volume, or the zone that I'm measuring in, if I have my wires very far apart, my spatial resolution is not going to be very good. And so that means if I have two pits very, very close to each other, I can easily image those as a single event. So the goal of research for many years was to continuously take those two wires and make them closer and closer and closer together, and still trying to extract the signal from them. But if you look at potentiostats or you look at your DDMs, we do a very good job of measuring currents. Currents can be measured to femtoamps and sometimes even attoamp type of resolutions. From a voltage measurement standpoint, the voltage measurements are typically millivolts or microvolts of measure. And so if you're thinking about the voltage drop that exists between two wires in solution, it is minimal. If you think about if you took your reference electrode and moved it in space, only a couple tens of microns, how does your solution resistance change? It's that small amount that we're trying to extract. So as research evolved, we started putting the probes closer and closer and closer together until we started running up against the wall the ability to make a measure with high spatial resolution and with enough electrochemical sensitivity. Here comes SVET, the Scanning Vibrating Probe, Scanning Vibrating Electrode Technique that replaced SVET. And why was that? So instead of using a 2-electrode probe, it's now reduced to a single platinum wire. You can see the advantage there is that my spatial resolution is as good as it can possibly be in a single wire versus a dual wire type of a probe. So how can I measure voltage, which is a relative measurement? How can I make that relative measurement with a single platinum wire? And the answer to that is I'm going to vibrate it. I'm going to vibrate it in Z. I'm going to move the probe up and down in Z. I'm going to make a delta voltage measurement at a fixed XY, record that value, and move it to the next XY position. What does that buy me? Why would I do it like this? I'm going to do it like that because I'm going to vibrate that probe in AC fashion. To put some numbers on it, typically it's an 80 hertz vibration, about 30 micron peak to peak. So then I can use a lock-in amplifier. And a lock-in amplifier is a device that's going to take an AC signal in, and it's going to output a DC voltage that's proportional to that AC signal in. So I get to use that lock-in because I know that anything that's coming in at 80 hertz with the fundamental frequency of vibration there, anything that's coming in at that frequency is going to be good signal. Everything else is noise. And so if we think about noise, it's generally randomly distributed and got the frequency spectrum. So if you took a noise versus frequency graph, it's going to be shown at every frequency. Now, in your particular lab, you may have a higher noise at the 50 or 60 hertz at your mains frequency. So we're going to select a frequency there that is away from that value. So that's why we defaulted to an 80 hertz type of a frequency of vibration. I'm going to vibrate that at that frequency. I'm going to use my lock-in amplifier that knows the frequency of vibration. And those two frequency waves are going to multiply together, and they're going to become a strong signal. And what that's going to do is it's going to make it 1,000,000 times more sensitive, 1 to the 6 times more sensitive than you can make without that lock-in amplifier, without employing technology. And so part of the SVET system is our Signal Recovery 7230 lock-in amplifier that has best-in-class specifications for making these types of measurements. So here are some figures adapted from a paper in Electrochemical Guide. And what we've done, what the author of this paper showed is on the far left-hand side, you've got a local anodes, cathodes, and the left-hand image is a current distribution from the anode to the cathode. The right-hand image is the resulting delta E in solution because of that current flow. And so we can see that the delta voltage kind of extends from that local anode, and that's really what I'm going to come in and measure. Those lines are called equipotential lines, meaning that everywhere on one of those lines all has the same potential. And so you can see once I get over the anode and I vibrate the probe in Z, you're going to see a difference between those. There's going to be a difference between those two equipotential lines. So I'm going to record that as a delta E voltage. How does all this happen? It's the true mechanics are over on the left-hand image, but some high-level summary is on the right-hand side. The probe is connected to something called an electrometer. So electrometer is going to measure the voltage. At that point in time, it's measuring everything that's coming through the probe, and that is both the signal and the noise. So that electrometer is then, it's a preamplifier, and so it's going to gain up that measured response. And again, that response is the signal from the signal and the noise. So that is now gained once it comes through the electrometer. The next path in the signal chain is going to go into a lock-in amplifier. Now it's going to be our Signal Recovery 7230, and we're going to use sensitivity settings to reduce the noise component of that. So imagine we have a very low noise and a very low signal. We have then gained the signal and noise up anywhere between 1 and 10,000 times. And now we've reduced the noise component. So now I'm left with a very high signal. That's going to go through some more filtering to remove noise further. That vibrating probe output is recorded. Then I'm going to move the probe to the new position. So in doing so, this is what the data is going to look like. This is a graph on the y-axis is voltage. On the x-axis is distance. So what can we see about this? First, let me tell you what the sample is and how we did this experiment. Took a 200 micron gold wire and a tap water, which is here in my laboratory about 150 microsiemens per centimeter. And we applied a current to the gold wire. So why did I apply a current? Well, gold's a noble metal, and it's not going to corrode in tap water. So I need to force this gold wire, force a current through the gold wire, and that's going to simulate a pit or some localized corrosion event. So think about I've got a large 32 millimeter epoxy disc, and a 200 micron gold wire is inserted into that disc, and I'm going to force a current through that gold wire. That's going to create a voltage field in solution, just like if it was a localized pit event. So when I look at this graph, I notice two things really. One, let's first talk about the magnitude of response here. The peak is 1.6 millivolts. So if you look peak from background to peak, it's a 1.6 millivolt signal. So even if I'm applying 10 microamps through a 200 micron wire, that's about the size of the field that we're looking at. So the field measurements are going to be very small. Then if you look further and think about not just from the signal, from the background to the peak, but look at the deltas between each and every data point is going to be in the microvolts or even nanovolt range. So you can see the value of good measurement electronics from your electrometer and good characteristics of your lock-in amplifier to reduce the noise. Second, look at the distribution of the field, and I think this is incredibly interesting. The units on the distance axis down there are from 0 to 8 millimeters. And so where do we start seeing the response of the field? Now, an analytical chemist is going to tell you that you're going to start seeing it three sigmas or 3 standard deviations away from the background. If I just look at this, I could say that I definitely start seeing a non-background response at the 3 millimeter mark. And then over, I continue to see a non-background response until I get over to a 5 millimeter mark. So that's about 2 millimeter response of the field. So why is that important, or what's interesting about that? Well, I know I have a 200 micron gold wire. I know that because I built the sample and it's got a 200 micron wire in it. But that 200 micron wire is generating a 2 millimeter or 2,000 micron size field. So we remember when we're doing these techniques, we are not imaging the pit itself. We're not imaging the local site. What we're imaging is the field created by the local site. And that's really important to think about. It's important because we could use an optical microscope to visualize the size of that pit. But what you could not do, and what you need a technique, a localized electrochemical technique to do, is to image the intensity of the pit. Maybe the pit's very large but not intense and passivated. Maybe it's very small but very intense. So this tells us that a single pit will visualize, maybe in this particular example, 10 times larger than it is itself. So when we start looking at resolutions, a single pit in a small background, if it's intense enough, we'll be able to measure it. But this also will tell you, if you have two pits that are very, very close together, the precautions that you need to take so that you don't visualize those as a single event. But we're going to take that one line scan shown here. This was a one-directional line scan. So the probe only moved in X and did not move in Y. And so at that point in time, I can graph these two parameters in a single chart. I don't need a data map. But as I start incrementing this in Y and creating a data map, I need a third parameter to graph. At that point in time, this is where we bring in the data maps and the color bars. So what we have here is a three-dimensional graph on X distance, Y distance, and then potential in the Z axis. And then we have a color palette at the bottom that's going to give you the values of these responses. And this is fully integrated rotational software into the data acquisition system, so we can rotate that around and flip it upside down. And what's nice about that is when you have pits that may have a negative current, they may be hard to see in the background, and we can take those and flip those upside down. You can kind of see them pop up as peaks and not valleys. So when I give that talk or when I have these discussions with a lot of new users and experienced users both, they tell me that, okay, SVET measures a voltage drop in solution. And when they go and they will understand this, but when they go and explain this to other members of their team, the other members of the team are looking for a local current flow, not so much a voltage in solution. So we're tasked with how do we correlate the voltage measuring in solution, which is the true output of a SVET experiment, and how do I correlate that to a measured current at the surface? So again, I get to employ that gold wire test sample, and I'm going to apply different current levels to that piece of gold. First, I did 10 microamps, and then I started reducing that value. And what that's going to do then is I'm going to plot on the y-axis the maximum measured voltage, and on the x-axis the amount of current that I applied to get that measured voltage. And we can do a linear fit. And we can see that we get a equation, just a y equals mx plus b, like you would in any linear fit. Then that is the equation we can then use to correlate max measured voltage or measured voltage to a current density at the surface. You can notice the linearity of this. You can also notice that this stayed linear even down below the 25 nanoamp applied currents. So this function is a way that you can account for your solution conductivity and account for your probe to sample distance and account for your electrometer gain settings and all of these different impact values and correlate your measured voltage to an applied current or to a current at your surface. So those are some uses of this applied gold test sample, and that's a very good tool to use to start learning how to do these experiments and how to prove them to other members of your team. But how do we take that knowledge in that training session, and how do we use this in a real type of experiment? So I was sent to our demo lab. At our demo lab, I was sent a sample from a car manufacturer. Told very little about what the sample was. So it is, mounted the sample up, and first we're going to do a large scan area, or what to me, what is a large scan area? And it's 16 millimeters by 12 millimeters. Since I don't know where the corrosion sites are, since I don't know their intensity, so I'm not sure how to set the lock-in settings and electrometer gain settings and condition that signal, I'm going to take a pretty fast scan just as an exploration. And so I'm going to do this 16 by 12 millimeters. I'm going to do it at 200 by 200 micron points, which is not the highest resolution of the system. I'm just looking for a quick exploration. And I can run that experiment in about 1 hour. Here I use a platinum iridium probe, and the dimensions of this come down to a couple microns at its tip. But if I go back here, on the far left-hand side, we can start seeing a corrosion event happen. We can start seeing that this signal is high, where all the rest of them are kind of background passivated signals. So what's exciting then is we did some time-resolved corrosion images. And so these corrosion images were taken with no delay in a simple loop in the VersaSCAN software. And what we did is measure the same area. So we zoom in on that one area of activity and take that image over and over and over again. And so each of these images took 1 hour. This is essentially after time equals 1 hour, time equals 3 hours, time equals 5 hours, 10. While I did not do any delays between the events, I'm only showing 6 of the 15 graphs, so there's inherently a delay between the images you're seeing. Another comment is that you see a lot less pixelation in this image. Because I'm looking at a smaller area, I can look with smaller pixels. So these were 50 microns by 50 microns. So the amount of data in this plot is 4 times the data density in the last plot. So that's why the pixelation looks a lot better. And so people use that word, they'll look at this and look back at the previous graph, and they'll say these resolutions are a lot better. I kind of define this as pixelation because I think about resolution as spatial resolution, electrical sensitivity, not necessarily just how clean and pretty the image is. But if we look at image number 1, time equals 1 hour, we can see at the top, we can see an intense site, and then at 3 it starts to passivate, and at hour 5 it's functionally completely passivated and gone. And then we can start seeing new corrosion sites on, for example, in the 5th image on the far right, we start seeing that pit starting to form. And so what you can do then is you can see the active areas passivate while others initiate, and you can literally watch the corrosion process happen. And this is a powerful representation to other members of your team to show, demonstrate how this is happening, how this changes throughout the course of exposure time, and how many pits do I have, and which ones are the most intense, because then we can take this information and use it with some optical measurements to determine the size and number of pits, and we can see you use this to determine their intensity. So here's another galvanic couple and different type of experiment. This has got the same type of strategy. So on the left-hand side, we have a large evaluation of area scan. This is a galvanic couple of another industrial customer of ours. And so this is a 12.5 millimeter by 12.5 millimeters of a square size scan and 500 microns by 500 microns point. But once we find the area of interest, we can go back and look at that small area of interest with much smaller data points. So now I've reduced my data point from 500 microns to 50 microns, but in both directions. So functionally, I have 100 times more data density on the image of the right than I do the image of the left. And you can see that the pixelation is a lot less as well, because I'm looking at a smaller scan area. So a lot of how long do these experiments take, a lot of where can I get, how do I tune the signals, this kind of stuff, are accomplished by these large scan area exploration evaluations. And then once you find them, we're going to go back into the area of interest and scan them with a higher resolution. A parameter of interest, a parameter of the experiment that we've touched on a little bit through this discussion that we'll come back and really draw attention to is optimum solution conductivity. And from a practical standpoint, this really has a large impact, so I want to spend some time talking about it. What is the impact of solution conductivity on the results that you can expect to see from a SVET experiment? If your solution is very conductive, seawater, your 3.5% NaCl solutions, what's going to happen? What's the consequence of this? Well, first, the V is going to be very difficult to measure. If V was IR, and if R is functionally the inverse of the solution resistance or solution conductivity, so if R is very, very low in one of these highly salt environments, I times R is going to be low, and therefore our V response is going to be low. So that's just going to make it a little bit more difficult to measure the low signal. But that's not the real difficulty. The real difficulty is the potential gradients become very dispersed, and it's going to negatively affect your resolution. And so when we go back and we think about the figures that I adapted from the paper and Electrochemical Active that show the equipotentials lines, how quickly does this disperse? If the solution conductivity is very high, it's going to disperse very quickly. If we can use a reduced conductivity environment, it's going to stay localized. That's going to improve both my spatial resolution because of the distribution and my electrochemical sensitivity by giving me a larger signal to measure. Here's another component of this as well. We talk about the activity of your sample. If your sample is highly active, what can happen is it can change during the course of the experiment. So if these experiments are 1 hour long, how does that impact it? Is your sample in the same state on the last data point as it was on your first data point? So what using a more resistive, not DI water, but a more resistive environment, what's going to happen is I can increase my V signal, I can keep that localized, I can fundamentally or functionally freeze the corrosion process. So I can investigate it and look at it with the sample being in a similar state at the end of the experiment as before the beginning of the experiment. But I still get the question of, what does this mean that you cannot make this measurement in seawater, or does this mean that you cannot make these measurements in highly conductive media? And that's not true. But so what we've done is come in and change the conductivity of the solution and take some different types of images. The first thing you can see is just obviously as you move from the top left, which is 122 microsiemens, the top right, which is 600 microsiemens, bottom left at 1400, and then 4000 microsiemens, we do start to lose visibility and clarity to that image. You can also see the scaling. The scaling of each one of these images is set to auto scale, so the top left-hand image is the peaks at 470 microvolts, and then 320 microvolts, and then 69 microvolts, and then at the last peak, it's 49 microvolts. So that speaks to the difficulty from a electrochemical sensitivity and difficulty from spatial resolution on the solution conductivity. So again, one of the big advantages of the VersaSCAN platform is once you have the VersaSCAN base in place, which includes the positioning system, the optical base, the computer, the installation and training, what we can do is just marry different types of measurement technologies on the front of this system and partner that with different Amatec manufactured measurement technologies to make different types of scanning experiments. Each of these scanning experiments have the same goal of trying to provide spatial resolution to electrochemical or materials measurements. But they all have different resolutions and they all have different key applications. So again, the SVET application is going to be recommended for galvanic couples and localized corrosion techniques. Scanning electrochemical microscopy has an incredible number of different types of applications. That's because it has as many applications as the field of electrochemistry. Because we have potentiostats and because we can control both the sample and the probe at different polarized potentials in different cells. But some common ones are sensors, fundamental research, so electrochemical kinetics, this kind of work. and really any kind of mechanism investigation. Localized impedance spectroscopy. So I'm going to take all the advantages of EIS and its ability to separate the current flow and assign it to different mechanisms within my sample. I'm going to use all the advantages of EIS in a localized fashion. So the same type of applications that benefit from EIS would benefit from LEIS. Scanning Kelvin probe. This is measures work function difference in air and non-destructive capacitance method. It's a very nice method in the fact that it has a way to just determine exactly how far away you are from the sample surface, that it's non-destructive, so we can oversample and get very, very clean images. And you can use this sample and you can use that sample for another type of test. Scanning droplet cell is going to confine electrochemistry growth to a single flowing droplet. And so what's going to happen is you're going to position a Teflon head very close to the sample surface and renew the solution and just study that electrode-electrolyte interface, or just studying electrochemistry within a drop. Then the optical surface profiler is a laser-based technique that can be used for a couple of different nice applications. One is to chart the topography, so it gives you another piece of the puzzle, like we're saying, of the depth of fits in this type of application. It can also be used as a highly precise and accurate level for leveling of your samples. And it can also be used in combination with other electrochemical techniques in something called constant distance mode imaging. And what happens there is first you map the topography of your sample. So if we envision like a weld is a good example of this. So we've got curved, complex topography type experiment. If you came through with a SVET probe and measured that at a constant Z, what's going to happen is you're going to get a high intense response from positions in the weld that are close to the probe and a low intensity that are far away from the probe. So you've convoluted your answer with two different mechanisms. What would happen with the SVET combination with OSP is we could first measure the complex topography with the OSP, then go back and use that as a background file, and the software will increment the SVET probe in Z as it's scanning the XY position and maintain a constant distance away from the sample. Another option that we have is the Faraday Cage that encloses the entire base. So we can put all the measurement, like all the samples and positioning system, inside of a large Faraday cage. And this is going to improve low current measurements and eliminate EMI noise. So in summary, samples are often non-uniform. They contain local anodic and cathodic sites or defects in coatings. Generally, samples are always non-uniform. If it's not a single crystalline phase of gold or highly polished type of sample, it's going to have some kind of non-uniform nature. Localized measurements complement bulk techniques by adding spatial resolution. And I think that's an important step. I would not present to you that SVET should be the only piece of your electrochemical corrosion or your corrosion studies. I think this tells one very valuable piece of the equation, but so does the Taffel plots, and so do secular polarization and LPR and galvanic corrosion, the different types of electrochemical corrosion measurements, but also weight loss and atmospheric exposure and these other types of non-electrochemical lifetime tests. So I think all three of these kind of go together to give a picture of what's happening in the corrosion of your system. And different scanning experiments have different applications and different resolutions. So thank you for attending this webinar. And if you need any more information on this specific technique or product used here, you please contact us at either www.princetonappliedresearch.com or by email at info.pari@amatech.com.